Hey, what's up, guys? This is Chung here. So this time, let's take a look at LeetCode problem number 397, integer replacement. So, given like a positive integer n, you can apply one of the following two options. The first one is that if n is an even number, you can replace the n with n divided by 2. Basically, if the n is an even number, you can cut the number by half. And even if the n is an odd number, you can either increase the n by 1 or decrease the n by 1. Pretty straightforward, right? And then it just asks you to return the minimum number of operations needed for n to become 1. So then it gives you some examples here, right? So for example, for a to become 1, we need 3 options. We just keep applying the options 1 here. 7, we have 2 ways of decrease it to 1. That's why we have 4 here. And here's some constraints here, right? As you guys can see here, so n is pretty big, right? 10 to the power of 31. So something like a max integers, right? And how can you do it, right? So every time you guys see like the minimum numbers of our operation, minimum answers, right? Always try the BFS, right? Or DP. And it happens to be, or actually the BFS, the DP, or the binary search, or even a sliding window, I think. Yeah, you can even you use a sliding window to do a minimum and maximum, right? And for this problem, it happens to be both the BFS and DP will will both work. So I'll implement both of them. And so the first thing is the BFS, right? So for the BFS, I think many of you already know the template, right? So it's just that at the beginning we have n here, right? And then we have seen set, right? So actually, so before implementing this thing, implementing either BFS or DP, so one thing to be noticed that, someone may have this question, since the n is very big, right? And if we just have this options 2 here, if we only decrease or increase, let's say if we only decrease this number by 1, it's going to take a linear time for us to decrease the number, right, into 1. So wouldn't that be TLE? The answer is no, because we have this one more constraints before that. We only decrease or increase by 1 when the number is odd. So which means even though we have a huge number, let's say we have a 9999, right? So let's say we have this huge number here. Yes, so to decrease it by 1, we decrease it to 81. But once this one becomes a pot, even numbers, we can then apply the rule number 2 here, which means we'll cut this number in half. So it means that our time complexity will bound it with this log n and not on, because every time when we have an even here, we'll cut this number in half. So that even though in the BFS, we'll always have like a pretty huge number somewhere following the n1 here, but the next time, the next time the number will become much smaller. I mean, smaller by half, right? That's why we can reach the answer in log n time, not O(n) time. All right, cool. So let me continue this BFS template, right? So we add n, and then the BFS here is like this, right? So for me, someone prefer to store the answers or the steps within the queue here. But for me, I personally prefer to use a for loop. to help us track the steps so that we can save some space in this queue here, right? So that's why I'm going to use the for loop in range of queue, right? I mean, we have implemented this BFS search many times, so this should be a no stranger to most of you, right? Pop left, and then so the template, right? So it's always good habit, to finish the template so that you will not forget later on, and in case you got distracted while implementing the inner loop here. So that's that. Okay, now the base case, right? So if the current one is 1, right, then we simply return the answer, right? And then we have like if the two cases, basically if the current mod 2 is not 0, it means that it's an odd number. So and then we can try this n plus 1 and n minus 1, right? And before doing that, always do a sanity check. If this thing is not in scene, right? Then we do a q dot append current plus 1. Okay, no, we don't need another bracket here. Same thing for the minus 1 case, right? Then we do a minus 1. So scene dot add current plus 1. Then down below here we have current minus 1. Okay, so this is the odd case, right? Odd number. Else even number, right? Pretty straightforward. Even if the current divided by 2 not in scene, right? And then we do this. I'll just copy and paste here, right? This thing here, and then that. Yep, I believe that's pretty much it is. Okay, let me run the code here. All right, accepted, submit. Cool. So it accepted. So that's the BFS, pretty straightforward, right? And then the next one is the DP. So for DP, it's also like pretty simple, But one thing to be noticed that, for DP, we usually have like either top down or bottom up. And for this problem, it's one of those problems you can only solve it by top down, right? Because for bottom up, the issue is that for bottom up, we have to loop through. We need to have a for loop from 1 to 2 to the power of 31. That will definitely TLE. But with the top down, it can greatly reduce the scenarios we will explore. That's why I'm going to use a top down here. So the current, right? And then I'll just use the Python sugar here to help us save few lines of code cache, right? So that's that. Okay. So and then we simply return the DPN, right? So here we have I think the base case is pretty straightforward, right? So if the base case, right? If the current one is 1, then we don't need to do another operation. Basically, the DP here it means that with this number n here, for this number n to become 1, what is the minimum operations it needs for this current number to become 1? Okay, and when the current number equals to 1, then we know we don't need any operations anymore, so we can simply return 0. Otherwise, right, so since we're asking for the minimum values, I'm going to initialize this answer with a maximum, and then the rest is just similar. We just also need to explore two scenarios, right? So the first one is the odd case, right? So if this that, and then we have a answer equals the minimum of the answer dot DP. So this is the odd case. It's going to be current one plus one, and then we plus one, because the plus one means that we are going to do either doing one operation, right? That's why, or the DP current minus one plus one, right? So that's that. Else same thing, right? We do a minimum of answers dot DP current divided by 2 plus 1. So yeah, I think that's it. So in the end, we simply return the answer here. I mean, so this is a very kind of unusual for us for in the DP solution, because usually when we have a DP, especially when the number keeps decreasing, we are only expecting current minus one, right? Because for the current plus one, if we keep doing it, we will never end, basically, So if there's a branch that the number is going in the opposite direction as our base case, it will TLE, it will stuck in the infinite loop. But like I said, since we have a condition for this DP plus one, is when we only do this DP plus current plus one or minus one when the current one is the odd number. And even though we're increasing this by one, but for that number, the next time that number will become half, because it will not go into the to this if branch the next time. Cool. So I'll just run the code here. Yeah, accept it, submit. So yeah, it also passed. All right. So, and I think for both of the solutions here, the time complexity is they're both O of log n, log n. Yeah, because we have this divided by 2 scenario, right? And the time complexity is bounded with this one. Yeah, I think that's pretty much everything for this problem. It's a pretty standard BFS or DP. Either way is fine. You guys can choose which way you guys prefer. But I think I personally always prefer the BFS as long as it's applicable, right? Because it's easier to implement. The template is more straightforward. The DP one, I mean, you can still do it, but for the DP one, just be careful. If you don't have this kind of special constraints here, it's very easy to end up in an infinite loop, or it'll TLE. Cool. Thank you so much for watching this video, guys, and stay tuned. See you guys soon. Bye bye.